Okay, we are going to do a quick review of quadratic functions, just the basics of graphing, sections 9.1 through 9.4 before our first quiz. So I just have a few things that we need to go over. So first, let's just look at examples of quadratic functions. How do I know whether it's a quadratic function? Well, if a graph is given, then it's going to be a parabola. Remember, that is just your basic shape of a kind of a funky looking U. And remember, they go up forever. They could also go down. Okay, they cannot face sideways. So that one can't happen. That's not a parabola. It's not a quadratic function. Okay, we can look at the equation. They will be in the form of either y equals, or in true function notation, f of x equals, and you have to have an x squared term. Now, the x term and the constant term can exist, but you have to have an x squared. No greater, we can't have x to a higher degree, like a third power or fourth power, and no lower, because that's linear, if I just have an f. Okay, so I mean, it could just be as simple as f of x equals x squared. Remember, that's our parent function. A basic parabola goes through 0, 0, and it grows pretty normally. The other thing that they might ask you about is from a table of values. Now remember, the x difference has to be constant, just as in the linear. The y difference had to go to the second difference. I'm not going to do an example of that right now. Your book has a great example, so go there if you need an example in section 9.1. But remember that first difference in your y values, don't worry when it turns out to be different, because it needs to be different. If it's the same, it's linear. So hopefully that y difference is different so that I can go and find the second difference of those values and see if that's constant. So look in your book. And I have a little note over here. When in doubt, create a table of values and graph it. Okay, so if you're not sure and you're given a table of values, then graph it. Okay, or if you're given an equation, create the table of values and graph it. And then hopefully you can tell it because it's a parabola facing up or down. Okay, that leads us into graphing quadratics. Okay, how do we graph them? There's 6 steps. I just wrote down the 4 steps because step 5 and step 6 is plotting the points and graphing. So step 5 and step 6 are going to be over here on the graph. Okay, so I just have a quadratic equation, a quadratic function here. Y equals x squared minus 4x. My a value is 1. My b value is negative 4. My c value is 0, and that's important. Okay, first step, axis of symmetry. My equation for axis of symmetry is the opposite of b over 2a. So come back up here. A is 1, b is negative 4, c is 0. Label those on my equation. So let's solve for this axis of symmetry. The opposite, and I just put that opposite out in front. Now, b is negative 4 over 2 divided by a is 1. Okay, so that's just 4 divided by 2 is 2. 2 negatives make it a positive. So I'm over here, a positive 2 axis of symmetry. All right, next up, find my vertex. To find your vertex, you take your value of x that is 2, and I find my coordinating y value. So plug 2 into my equation. So x squared, so 2 squared minus 4 times 2. So 2 squared is 4 minus 4 times 2 is 4 is 0. That's not right. What did I do wrong? Oh, 4 times 2 is 8. Oh my heavens. Sorry guys, I'm not going to delete this on a video. You're going to see that. 4 minus 8 is negative 4. So my vertex, I plugged in my x value of 2. When you do the arithmetic correctly, you get a y value of negative 4. So step 5 says to plot your points. I do that as I go. So my vertex is at 2, negative 4. Okay, there's my vertex. My y-intercept should be over here on this side, and that's step 3 is to find my y-intercept. My y-intercept is my c value. My c value is 0. So it goes through the origin right there. Okay, step 4. Find 2 more points on the same side of the vertex as the y-intercept. I'm going to argue this at this point. I'm only going to find 1 more point. Okay. If your y-intercept is close to your vertex, then you'll probably need 2 more points. But because I'm actually kind of far away, I can start to see this general shape. I'm just going to pick 1 more point. And I'm going to go ahead and pick one out here. Oh, I don't want to go. Let's do -1. So my other point I'm going to pick is -1 in parentheses squared minus 4 times -1. It's important always to put that in your parentheses. -1 squared is 1. Minus 4 times -1 is -4, but I've got 2 negatives, which makes it a positive. So that's 5. So I picked the point -1 for my x, and when I plugged it into my equation, I got 5 out. So -1, 5. 1, 2, 3, 4, 5. Now, step 5 is plotting your points. Step 6 is creating that butterfly effect across the axis of symmetry. So I'm just going to mirror these. Since this point is 2 away to the left from the axis of symmetry, I'm going to go 2 to the right of my axis of symmetry and mirror that, so right along my x-axis. This is 3 away up here at 5, so I'm going to come to my axis of symmetry and I'm going to count 3 away. And now I've got a basic parabola shape. Come on in, sketch it in. Couple more things to think about. Zeros have a function. Zeros are a function where it crosses the x-axis. So if I go back, we'll just use this graph that I have. My zeros of this function would be where x equals 0 and where x equals 1, 2, 3, 4. How do I know that those are zeros? If I plugged 0 or 4 into my equation, I would get 0. Okay, so let's just do 0. 0 squared minus 4 times 0, 0. Let's just try 4 really quickly. 4 squared minus 4 times 4. 4 squared is 16, minus 16, 0. So my zeros of my function are where it crosses the x-axis, and when I plug those x values into the equation, I get 0 out. That means I haven't moved up or down along my y-axis. Where will I use these zeros in real life? If I'm looking at the path of a ball, or if you're throwing something off of a cliff, or anything that makes a curved pattern. Okay, say you throw something off of the building, you're doing the egg drop in science, and you throw your egg drop off of the building, I get a nice curve, and I want to know, when does my egg hit the ground and hopefully not break? It's going to hit the ground right there where I model time versus height, and this would be my time in seconds, and it's probably going to take a fraction of a second to maybe a second. So that's the trick to this. If you plug in 1 second into your equation, you're trying to find zeros, you get 0 out of it, that's your 0. It takes 1 second for that object to fall. Okay, and the last thing that we have to talk about is what do the A, B, and C values represent on a graph. So if I have my quadratic and I'm looking at it in the form of ax squared plus bx plus c, how do these values change my graph? The A value tells me how narrow or how wide it is. Remember, it's backwards thinking. A big A value makes it grow really quickly and makes it really skinny. A small A value between 0 and 1 makes it grow slowly and opens it up really wide. We're looking at the absolute value. The positive or the negative doesn't matter as far as the width. The positive or the negative tells me whether it opens up or down. Positive A opens up. Negative A opens down. Okay, the C value is my y-intercept. That tells me whether my graph gets shifted up or down. Okay, if it's a positive C value, I'm shifting it up. If it's a negative C value, I'm shifting it down. Okay, and lastly, this B value, we didn't talk a lot specifically in the first part of this, but my B value shifts something. If I come up here, the only equation I have so far that uses a B value is the axis of symmetry. And look, this equation has a B value, and I've shifted it sideways. So my B value shifts axis of symmetry, which really does the whole parabola sideways. Okay, I hope that review helps. Hopefully you've done the review in the book. Maya's making a bunch of noise. Good luck.